Hello, welcome to this lesson. In this video, I'm going to learn about the phase relationship between voltage and current in a pure ohmic resistor circuit. But before we do that, I want us to talk a bit about impedance. So just like we have in DC circuit an opposition to the flow of current, we have the same thing that happens in AC circuit also. But in AC circuit, we term this opposition to the flow of current as impedance. Okay, and then this opposition to the flow of current in AC circuit is caused as a result of the combined effect of inductive, uh, capacitive, and then resistive elements. Okay, so the combined actions of these three elements results in the opposition of the flow of current in AC circuit. So this is termed as impedance. And then it is normally represented with letter Z. Okay, so throughout this course, we are going to use Z to represent impedance. And then, like I said earlier on, it is caused as a result of the combined effect of inductive reactance. Okay, inductive reactance, inductive reactance. Active reactance, we have inductive reactance, capacitive reactance, and then resistance. So the combined effect of all these three uh, gives the impedance. And then the inductive reactance is caused by an inductor. Okay, it is caused by an inductor. And then the capacitive reactance is caused by a capacitor. And then the resistance is caused by a resistor. Okay, so normally the inductive reactance is represented with the symbol XL, and then the capacitive reactance is represented with XC, and then the resistance is represented with R. So that's to say that the combined effect of the inductor, capacitor, and the resistor provides the opposition to the flow of current in AC circuit, which is termed as impedance. Okay, so now let's talk about the phase relationship between uh, current and voltage in a pure ohmic resistor circuit. So I have this circuit here where you have an alternating voltage source, and then you have current I here, and then you have an ohmic resistor here. So you're going to look at the phase relationship between the voltage and current in this circuit. So you've been given the voltage V to be equal to Vm sine omega t. Okay, and then omega is angular frequency, and then this time here, this t is just time, and then Vm is the peak voltage, and then V here is the alternating voltage or voltage at time t. Okay, in this circuit. So the current in this circuit at a particular time is given as I. Okay, and then what will happen is that when this voltage starts flowing through the circuit, there's going to be a voltage drop across this resistor. Okay, so let's take that voltage to be VR, and then this voltage will be equal to the current flowing through the circuit times the resistance, which I represent with R. Okay, so because the resistor is the only element in this circuit, the total voltage from the voltage source will be equal to the voltage drop across the resistor. So you're going to have V to be equal to VR, okay, which is equal to IR. But you know the value for V, so you can do the substitution here. So when I do this, you're going to have Vm sine omega t equals IR. Okay, so what we're going to do next is that you want to compare the current value to the voltage value, or the current expression to the expression for the voltage, so that you see you will be able to tell the phase relationship between them. So for us to be able to do this, I will have to make the current the subject. So I'll divide both sides by the R, then I'll cancel this out. So when I do this, you're going to have the current to be equal to Vm sine omega t over R. Okay, I'm going to rewrite this as I because Vm over R sine omega t. Okay, and this Vm over R, okay, is the peak current. So we have peak current Im to be equal to maximum voltage over the resistance. Of course, when you have the maximum voltage being divided by the resistance, then that means that you are going to get the maximum. Okay, so what will happen is that this current I here will be equal to the peak current, which is Im, if and only sine omega t is equal to 1. Okay, so what will happen is that assuming you have sine omega t to be equal to 1, then you are going to have the current I to be equal to Vm over R times 1, which is the same as I equals the peak current. Okay, so we are going to get the instantaneous current I to be equal to the peak current if sine omega t is equal to 1. So let's take note of this. So from here, we can see that the instantaneous time I will be equal to Im sine omega t. Okay, so this is what you have now. So now what you can do is that you can compare this expression for the current to the expression for the voltage that was given. So you have the voltage to be equal to Vm sine omega t. Okay, so this is what you have. So when you are comparing these two, you see that we have sine omega t here. Let me indicate this with a different color. We have sine omega t here. Then we have sine omega t here. Okay, so you see that they are all the same. The only difference is the peak current and then the peak voltage. That's what differentiates these two expressions. So this tells us that the current and then the voltage are in phase. Okay, for this pure ohmic resistor circuit. So we conclude that in a pure ohmic resistor circuit, the current and then the voltage are in phase. The only time that the current and the voltage will not be in phase will be, let me use this scenario. Let's say we had the current I to be equal to Im sine omega t plus pi on 2. Okay, and then we had the volume to be that same value Vm equals sine omega t. Okay, so in this case, you can see that we have a difference of what pi on 2 here, which is plus pi on 2. So that means that the current leads the voltage by pi on 2. So in this case, when we are asked that what is the phase relationship between the current and voltage, you see that the current leads the voltage by 90 degrees or pi on 2. Or in other words, you can see that the voltage lags the current by pi on 2 or 90 degrees. So that's how to tell whether current and voltage are in phase or not. Okay, so I'm going to use a figure to show the phase relationship between voltage and current in this circuit. So I have this figure here. Okay, so the dashed line or the dashed wave represents the current wave, and then the complete wave represents the voltage wave. Okay, so you see that they all have the same starting point. Okay, they all start at this angle here. So that tells us that they are in phase. Okay, it doesn't matter the maximum voltage value being higher than that of the maximum current. So far they are starting at the same point or angle, we see that they are in phase. Should you have a case where you have something like this, let's say this is the voltage and then uh, this is the voltage. Okay, and then we have the current to starting from somewhere here, okay. In this case, then we are going to see that the current is lagging the voltage or the voltage is leading the current. But at this point that they start at the same point, we see that they are in phase. But should it be that they all had different starting point, then that means that one is probably leading the other and then one is lagging. So that's all for this video. Please make sure you like the video and subscribe to the channel.